Before we jump right into talking about specific functions and commands in Solidworks, I'd like to talk about this design that we'll be working with throughout this course. I want to quickly walk through each of the features that we'll be creating so you have an idea of the roadmap of where we'll be going, and you can see how the design will come together from beginning to end. Any design you create in Solidworks is really just a combination of separate features. If we look over at the feature manager tree here, I can use this rollback bar to scroll back through the history of the part so that we can see how it was created. This part here was started with just a simple rectangular extruded boss. This extruded boss is a sketch-based feature, which means that the 3D geometry was created from the 2D sketch. Next, this tab shape was created. You can see that this is another boss extrude feature, and this feature was based off of another 2D sketch. Moving along, a cut feature was created on the tab part. This is a cut extrude, a feature that simply removes geometry, and we can see that it was based off of this 2D circular sketch. Next, a mirror feature was created, which replicated both the tab extrusion and a circular cut feature to create an exact copy of the same geometry. Next, 4 clearance holes were created for an M10 screw using the hole wizard feature, which we'll talk about later. And finally, 2 fillet features were added. The first fillet feature was just rounding off these corners here, and then a slightly smaller fillet was used to break all the rest of the edges. Now you may have noticed that most of the features in the tree were based off of 2D sketches, such as the rectangle for the base, the tab shape, and the circular cut shape. These are examples of sketch-based features, or, as the name implies, features that are initially created from a 2D sketch. The other types of features that you'll be working with are called applied features, where you're really just modifying the existing 3D geometry, as was the case with these fillets. Now I had mentioned earlier that every part in Solidworks is created using a combination of features. This means that for any design you create in Solidworks, there are many possible approaches that you can use to achieve the same geometry. To illustrate this point, let me switch to another part that I currently have open in Solidworks. Here, I'm holding down the Control key on my keyboard while tapping the Tab key to switch to this other part I have open. Now this part seems to look very similar to the part that we had open just a second ago. In fact, the part itself is identical in shape, but a slightly different approach was used to create the combination of features. Let's use the rollback bar in the feature tree to walk through how this part was designed. If we take a look at the very first feature, we see that again, a rectangular boss extrude was used. But if I expand it and look at the sketch, notice that it was created in a different orientation. So, right away, you can see how 2 varying approaches led to the same geometry. Moving on, the tab shape was again created. However, this time, the tab was extruded to the width of the overall part. If I expand this, you can see that the same sketch shape was used, and it was really just the feature itself that was created with a slightly different design intent in mind. Next, an extruded cut was used on a circular sketch just like we saw before, but this time, the hole was cut through the entire width of the part. And next, a second cut extrude feature was used to create the 2 tab shapes. If I expand this feature on the tree, you can see that just a rectangular sketch was used to make the cut. Next, the hole wizard holes were created, along with the 2 fillet features that we saw before. So this is a simple example of how the very same design can be created using a different combination of features, and it's really up to you to use the features that you feel most comfortable with. As you become more experienced using Solidworks, you will find that the design intent will start coming more and more naturally. To begin creating the base feature for the bracket, I'll press the File New icon. This will be a part, so I'll select the default part template and click OK. Since we're going to be designing the part using metric units, I'll make sure that the units are set to the millimeter, gram, second standard by checking the status bar here. At this point, we can begin our sketch for the first feature. Now, you saw a moment ago how this first feature could begin with a wide rectangle on the top plane and be extruded up to create the thickness. Or, it could be created with the thin rectangle on the front plane and extruded toward the sides to give it a width. For this example, I'll be sketching a wide rectangle on the top plane and extruding it up to give it some thickness. I don't necessarily have to sketch this rectangle on the top plane, however. I could sketch it on the front, top, or right reference planes, but you have to decide if you want the final part to look like this, or like this. If we want the part to look like this, we'll begin this rectangular sketch on the top plane. To begin the sketch, I'll click on the top plane and select the sketch icon from the pop-up menu. When I do, the graphics area rotates onto a normal 2 perspective, so I'm looking directly onto the top plane, and we can begin sketching. I'll first launch the rectangle tool from the shortcut toolbar by pressing the S key on the keyboard. For this design, I'd like the reference planes to pass directly through the center of the part, so I'll be using the center rectangle tool. I'll show you a little bit later how keeping the reference planes in the center of the part will help with some aspects of symmetry, and later, assembling other components once we begin talking about assemblies. When I begin the center rectangle, I'll make sure that the yellow flag appears next to my pointer, indicating that a geometric relation will be added on the origin for the center point of the rectangle. I'll click to begin, click again to give the rectangle a size, and press Escape on my keyboard to deactivate the rectangle tool. At this point, since the size of the rectangle is underdefined, we'll add a couple dimensions. I'll activate the Smart Dimension tool from the shortcut toolbar by again pressing the S key on the keyboard. I'll start with the length dimension by clicking on it. Click again to position the dimension in the graphics area, and type in 150 millimeters. I'll click the green check, and the dimension is added. For the width dimension, I'll click on this line here. Click again to position the dimension, type in 100 millimeters, and click the green check. At this point, the status bar tells us that the sketch is fully defined, and all the geometry turns black to indicate this as well. Next, I'll launch the Boss Extrude tool by switching over to the Features tab in the Command Manager and select the Extruded Boss Base tool. Here, I'll be using a blind extrude, so that the thickness of the rectangle will be going above the top plane. I'll type in 15 millimeters for the depth, and press Enter once on the keyboard to update the preview. The preview looks the way I want it to, so I'll click the green check to finish the feature. In this lesson, we'll be working on creating the tab shape. Up to this point, we've been starting our sketches on the default front, top, and right reference planes that are included with each part template. In addition to these, Solidworks includes a reference geometry tool that allows you to add reference planes. However, Solidworks conveniently allows you to use faces of the model to define the sketch plane. And when you have a face of the model, such as this face here, it's not necessary to create additional planes. To begin a sketch on the face of this model, I can simply click on the face and select the sketch icon from the pop-up here. Alternatively, I can switch over to the Sketch tab of the Command toolbar, and when I click the new sketch icon from here, Solidworks asks me to choose a plane, a planar face, or an edge on which to create a sketch for the entity. So I'll click this face here, and when I do, Solidworks puts us into Edit Sketch mode, as you can see from the status bar and these icons up here, and Sketch 2 is added to the Feature Manager tree. Since Solidworks didn't automatically rotate us to look normal to the sketch plane, I'll press the spacebar on the keyboard and click the Normal to View orientation so that I'm looking straight onto the sketch plane. Although the face of this model is a small rectangular face, it's really defining an infinite plane that we can sketch on. What I mean is, when I click the rectangle tool and define a sketch anywhere in space, if I rotate the model a little bit, you can see that we're actually sketching on an infinite reference plane which is defined by this face. I'll look normal to the sketch plane again by pressing the spacebar and selecting the Normal to View. To get rid of this geometry, I'll box select it and press Delete on the keyboard. Now to create the tab shape, I'll start by using the Line tool, which I'll activate using the shortcut toolbar. I'll begin the line so that the endpoint is coincident with this top edge of the model. Paying attention to the number next to my pointer, I'll make sure it's relatively close to the final size. Again, it doesn't have to be perfect. We'll use dimensions to define the actual size a little later. I'll click again to create the endpoint. And next, we're going to create an arc that connects this line segment to another angled line segment. Now, Solidworks does include an arc tool, as you can see here on the sketch toolbar, but I'd like to show you a nice shortcut that you may find very convenient. With the line tool still active, Solidworks provides a way to quickly switch to the arc tool simply by moving the cursor close to the endpoint of the line, and without clicking anything, simply moving the cursor away from the endpoint. Now you can see that the arc tool becomes active, and I can move this arc from one side to the other. Notice that if I want the arc to go below the first line segment, I can simply bring my cursor back to the endpoint and move my pointer off in a different direction. I'll go ahead and sketch the arc that I want, and then all I have to do is click to define the endpoint of the arc. When I do, Solidworks automatically brings us back into the Line tool. This is really convenient for creating arcs quickly when you're sketching a chain of lines. I'll snap the endpoint of this line onto the top edge of the model. And when I do, you can see that there are actually two yellow flags that appear. The coincident icon informs me that the endpoint is coincident with this top edge of the model. And a tangent icon appears to let me know that this segment will be tangent to the arc that we created. Finally, I'll close this profile by bringing my pointer back to the first endpoint. For the extrude feature, we'll want this to be a closed profile. I'll press the escape key to get back to the selection arrow, and you can see the green flags which identify the automatic relations that were added as we sketched. In case you don't see the tangent relations or these coincident relations, keep in mind you can add these manually as well. Let me give you a quick reminder. I'll delete this relation flag by clicking on it and pressing delete on the keyboard. Now you can see that the line is no longer tangent to the arc. If an automatic relation was not created, you can add it manually by selecting the arc and control selecting the line, and choosing the tangent relation from the pop-up or from the property manager. Next, we'll fully define the sketch using dimensions. To launch the Smart Dimension tool, I'll press the S key from the keyboard, and I'll begin by giving the tab a height dimension. I'll choose this line segment and the arc. And notice that Solidworks snaps the dimension onto the center point of the arc. I'll click again to place the dimension and type in 50 millimeters. In case you want this dimension to attach to the arc itself rather than the center point, you can actually move this endpoint of the dimension just by clicking and dragging. And you can see that Solidworks snaps into the new position. For our example, I'm going to keep the endpoint onto the center point of the arc. Next, I'll give the arc a radius value. I'll click on it, type in 25 millimeters, and press enter on the keyboard. Moving on, I'll create an angle dimension between this angled line and this horizontal line, and type in 75 degrees. I'll repeat this process for the opposing line segments, and produce an angle of 75 degrees. At this point, notice that most of the geometry is still blue. If it's unclear which dimensions you still have to add in order for the sketch to become fully defined, I always recommend pressing Escape on the keyboard to get back to your selection arrow, and then clicking to move the geometry that's still underdefined. I recommend clicking on a combination of points and segments to see what you're still able to move. In this case, our geometry is still free to move from side to side. The design intent of this part calls for the tab to always stay centered with respect to the base extrude geometry. So how do we accomplish this? Well, one approach would be to utilize dimensions. We know that the overall length of the rectangle is 150 millimeters, so we can create a dimension of 75 millimeters from the edge to the center point of the arc. Although this would be a sound approach, I would prefer to use geometric relations to ensure that the tab always stays centered, in case our base geometry ever changes down the road. To do this, I'll create a center line to use as a reference to make sure that this tab shape stays centered directly above the origin of the part. Notice next the line tool here in the toolbar. There's actually a drop-down arrow where I can choose from a line or a center line. I'll activate the center line tool. And to begin, I'll make sure that the pointer shows the yellow flag when I'm on the center point of the arc, indicating the geometric relation will be added. And for the next endpoint, I'll select the origin of the base part. Again, I'll make sure that the yellow flag appears for the geometric relation. To complete the center line, I can either double-click or press Escape to get back to my selection arrow. With the center line added, the geometry is still free to move from side to side. But if I add a geometric relation on the center line by clicking on it, I can choose to make this center line vertical. When I do, the geometry turns black and fully defined. By making the center line vertical, I can be sure that the arc is always directly vertical with the origin. Now at this point, the sketch is fully defined and we can move on to create the feature. But before I do, I'd like to show you a couple more tools in the sketch environment. In this example, I use 2 angular dimensions, but perhaps I want these segments to always have the same angle. If the design ever needs to change under our current dimensioning scheme, I would have to change both dimensions manually. To incorporate a little bit of design intent, let me show you another approach. I'll click on this dimension to highlight it, and press Delete on the keyboard. I'll press Escape to get back to my selection arrow, and at this point, you can see that this angle is now free to move. If I want to ensure that this line segment is always the same angle as this one approach is to use symmetry. I'll add a symmetric geometric relation by selecting this point here, holding down the Control key, selecting the center line, and with the Control button still pressed down, I'll select this endpoint here. With all 3 entities selected, Solidworks shows me that a symmetric relationship is possible. I'll click it from the Property Manager, and you can see this sketch turns black again. With this design intent, if I change this angular dimension once, you can see that both segments update to maintain the symmetric relationship. I'll switch this back to 75 degrees by double-clicking on it and clicking the green check. Next, let's move on and create the extruded boss. To do this, I'll switch to the Features toolbar and click the Extruded Boss Base tool. Whenever you're moving from the sketch environment on to create a 3D feature, I always recommend looking at an isometric view. You can rotate the part in the graphics area, or you can press the spacebar and click the isometric orientation from here. I recommend switching to an isometric view because it gives you a clear picture of which direction the extruded geometry is being added to. If I were to use the normal to view, you can see that it is difficult to tell what direction the arrow is facing, so I'll zoom out a little bit and rotate to give us a better perspective. Since the geometry is being added in the wrong direction for what we need here, I'll click the reverse direction icon here in the Property Manager. And since our first base extrude was using 15 millimeters, SolidWorks remembered that value and had saved it here in the Property Manager for us. I showed you in the first lesson how the tab shape was extruded to the entire width of the part. Since we know the part is 100 millimeters, I can type in 100 millimeters for the dimension and press Enter. But what happens if the width of the base extrude were to change at some point? If you change the width of the base extrude to 125 millimeters, SolidWorks wouldn't know to update this tab extrude, so you would end up with a 25 millimeter space on the side of the model. To incorporate some additional design intent taking advantage of the parametric capabilities in SolidWorks, another approach would be to use an end condition. Instead of blind, another common end condition is the up to surface option. When you choose up to surface, you can see this box highlighted in blue appear, asking you to choose a face or plane. If I select this face here, SolidWorks doesn't show you a value for the width of the extrude. It simply knows to always extrude up to this face here. This can be very useful, because if the original base feature were to ever change to a value other than the existing 100 millimeters, the extrusion width of the tab would also change to the new value automatically. For this example here, I'll switch back to use a blind end condition and enter 15 millimeters for the thickness. Taking this approach, I'll be able to show you a couple other features such as the mirror feature, and talk about some other ideas of design intent to get you familiar with it. So at this point, I'll click the green check in the Property Manager to finish the tab feature. In this lesson, we'll talk about how to add the circular cutout for the hole. To do this, we'll be using the Extruded Cut command. This will be another sketch-based feature, so we'll first need to create a sketch before we can create the actual 3D feature. Now I've shown you how you can create a new sketch by clicking on the default reference planes or on the face of the model. And up to this point, we've always started a sketch and then launched the feature. However, if I go ahead and click on the Extruded Cut command from the feature toolbar, Solidworks prompts us to either begin a new sketch on a plane or planar face, or use an existing sketch, which we have not created yet. So, to begin this sketch, I just need to pick a plane or planar face. I'll rotate the model a bit and sketch on this plane here. Again, notice we are now editing sketch 3 and the sketch icons appear, all indicators that we're in the edit sketch mode. This will be a simple circular sketch, so I'll launch the circle tool from the shortcut toolbar by pressing the S key on my keyboard. I won't worry too much about the placement of the circle here as I'm sketching, since I'll come back in a moment and add a geometric relation to position it. I'll click once for the center, and again for the radius. At this point, I'll press Escape on the keyboard to get back to the selection arrow. For the design intent of this cutout, we want to ensure that the circle is always centered about this arc here. There are a couple ways to do this. To add the geometric relation, I can select the circle, and while holding the Control key down, select the arc. This will bring up a pop-up menu that shows you the available relation options that are possible with these two items selected. I can make them co-radial, tangent, or concentric. Concentric is the option that I want to use here. When I select it, you can see the circle snaps into position. To show you another approach to adding the relationship automatically, let me delete this concentric relation. A second approach is to click on the center point of the circle, and we can snap it onto the center point of the arc. But first, we have to make it visible in the graphics area. To do this, with the mouse button still pressed down, simply hover over the arc for a moment, and you can see the center point appears in the graphics area. Now that the center point is visible, I can simply move my pointer near it, and when the yellow flag appears, we know that Solidworks is adding a geometric relation. Just to be sure, you can always press the Escape key to get to the selection arrow and try to move the geometry. You can see that the center point can no longer move and is fixed into its position, but the radius is still underdefined. To define the radius, I'll use a dimension, so I'll launch it from the shortcut toolbar, click on the circle, and place the dimension in the graphics area. I'll type in 20 millimeters and press Enter on the keyboard. Now that the sketch is fully defined, we can continue on with the Extruded Cut command. In the first few examples, I showed you how you can switch over to the Features toolbar and launch the Extrude feature. But since we began this sketch by launching the Extruded Cut feature, Solidworks automatically knows the sketch is going to be used for an extruded cut. So, if I simply exit out of this sketch, Solidworks automatically launches the Cut Extrude command. The Cut Extrude is very similar to the Boss Extrude. You have options such as choosing an end condition or a direction. But there is one option that I'd like to point out here. When you're working with cuts, a very common end condition is the Through All option here. Through All ensures that the cut will always go through the entire part. So even if the part width changes to, say, 200 millimeters, Solidworks knows to extend this cut up through the end of the part, regardless of the size. If I were to use a blind end condition, at this point, the 15 millimeter depth cuts through the entire tab. But if this tab were ever to change to, say, 20 millimeters, Solidworks wouldn't know to update the cut. So in this case, it's a good idea to use the Through All end condition to ensure that it always cuts through the entire geometry. At this point, I can click the green check, and the cut feature is added. To create the second tab component for the bracket, we'll be working with the Mirror feature to replicate existing geometry. I'll launch the Mirror tool from the Features toolbar, and the Mirror Property Manager appears. As you begin working with more and more functions in Solidworks, you'll notice that most property managers appear to be pretty similar from one to the next. Anytime you see an area shown in blue, this is an indication of an active selection window. And if you hover over the selection for a moment, you can see what Solidworks would like for you to select. In this case, Solidworks is asking for a mirror face or plane to select. Pay attention to which box is highlighted in the blue color here, so that you know what you should be selecting graphically. Since I would like to replicate this tab and the cutout shape to the other side of the base part, it's important that our mirror face or plane passes directly through the center of the part. This is the reason that I used a center point rectangle for the original base extrude feature, so that the default reference planes are in fact in the center of the part. Notice that when a tool is active, such as the mirror command here, you can no longer see the feature manager tree since it is replaced by the tool's property manager. However, when a tool is selected and the property manager is showing, it's still possible to access the feature manager tree. If I expand this text here in the graphics area, I can see all of our reference planes as well as the features that we've created up to this point. Since the mirror face selection box is active, I simply need to tell Solidworks which face or plane to use. Again, you can use faces of the model or default reference planes. If I hover over these planes for just a second, the different planes that were created appear in the graphics area, and you can see that the right and front planes pass right through the center of our part. In this case, we would like to use the front plane. Notice that after we select the mirror face or plane, Solidworks now activates the Features to Mirror selection window. Here, I can simply tell Solidworks which features that we want to replicate, but notice that there are a few other options below. Solidworks allows you to mirror features, faces, or entire bodies. For this example, I would just like to mirror features. So with the window active, I can select the features here from the Feature Manager tree, or I can select them graphically. If I select the cut shape and the tab, Solidworks gives you a preview of the geometry. This looks like what I want, so I'll go ahead and click the green check. And we can see that first the tab and cutout are replicated to the opposite side of the base. If you've been clicking and following along with each lesson up to this point, don't worry about following through each step we go through here in this lesson. I'd just like to take a couple minutes and talk about the idea of design intent and how Solidworks behaves as a history-based modeler. When we created the mirror feature, we mirrored both the tab and the cutout. Let's take a look at what happens if we edit this feature. I'll begin by clicking on the mirror component here in the feature tree and selecting the Edit Feature icon from the pop-up. What I would like to do is to remove this cut from the mirror feature. To do this, I'll highlight it in the Property Manager and press Delete on the keyboard. When I click OK, you can see that SolidWorks updates the mirror feature to only include the tab shape. But what if we want this cut to go through both tabs? If I come back and edit the Cut Extrude feature, you can see that SolidWorks rolls back. And at the point when this cut feature was created, the other tab was not created yet. So any changes I make to this cut feature will have no impact on the mirrored tab. I'll click the red X to cancel out of this command. Another way to visualize this history-based modeling is by using the rollback bar. If I roll back to the beginning, you can walk through each feature as it was created. So although our Cut Extrude feature is a through-all cut, the hole is only cut through everything that's been created up to this point in the history of the design. Since the mirror feature was added later, the through-all cut doesn't cut through the tab. Oftentimes, you may realize that you've created features in the wrong order. If you do, you may want to fix this problem by deleting existing features and creating them in a new order. Fortunately, however, SolidWorks provides some flexibility so you don't have to do this by allowing you to reorder features in the Feature Manager tree. So, in the case of the circular cutout, we may want the cutout to come after the mirror feature so that the cut goes through both tabs. To do this, I can click on it in the feature tree, hold the mouse button down, and when I move my cursor below the mirror feature, you can see that the cursor changes to show me that the features will be reordered. When I release the mouse button, the cut feature is reordered, and now the circular cutout goes through both tabs. Again, to help visualize this, if I use the rollback bar, I can roll back to the original tab shape, roll down to the mirror feature which mirrored the tab shape, and finally, to the Cut Extrude feature. If I edit this Cut Extrude feature, again we can see the through all end condition was used to cut through all of the geometry, including the mirrored tab, and I'll click the Cancel command to exit out of the feature. As you can see, the concept of design intent can be very important when you are designing a part or assembly in SolidWorks, and there are many tools that SolidWorks provided to help you achieve the design intent that you may want to achieve. In this lesson, we'll discuss how to add the 4 mounting holes for this bracket component. Now these holes can be easily created using the extruded cut feature using similar methods that we've already seen. But here, I'd like to show you some advantages of using the Hole Wizard feature. I'll launch it from the feature toolbar, and you can see that the Hole Wizard contains a library of predefined standard hole sizes, including counter bore holes, countersunk holes, clearance holes, tapped holes, tapered tapped holes, as well as another item called Legacy Hole, which is rarely used, and a variety of slots. The Hole Wizard saves you a lot of time when creating cutouts to be used with standard hardware, because it includes predefined hole sizes for most standard hardware, so you don't have to look up standard hardware hole sizes to size your cut features manually. Another advantage of using the Hole Wizard feature is that when you create a 2D drawing of this part, as we'll see in a future lesson, SolidWorks can automatically include the hole callouts and annotations for you. The Hole Wizard feature breaks down into 2 tabs, the Type and the Positions tab. Beginning with the Type tab, you can use the Property Manager to choose the type of hole you'll be using. In this case, it will be a simple clearance hole, and you can use the filters below to define it further. This will be an ANSI metric standard. You can use the drop-down here to choose from a few different drill types. In our case, this will be a screw clearance, and you can choose the size of the screw for this clearance hole. From the drop-down, I'll choose an M10 screw, which we'll be using in the assembly. There are a couple options for the fit type, which again are driven by the ANSI metric standard, as well as a couple other options such as the end condition. I can give it a depth, or as we saw in the extruded cut command, I can ensure that the Hole Wizard cuts through the entire part by switching this selection from blind to a through all end condition. I'll skip over the other options here for now and move on to the Positions tab. Here, we must tell SolidWorks where to locate the holes that we want to create by selecting a face. If you want to create holes on multiple faces, SolidWorks allows you to work with a 3D sketch, but that's a little bit outside the scope of what we're doing here. To keep this example simple, I'll select this top face to tell SolidWorks to place the holes here. When I do, notice that SolidWorks activates the point tool. These sketch points are what SolidWorks will use to define the position of the holes. I'll quickly create 4 points for the holes. I won't worry about the exact location quite yet, but rather simply click 4 times in order to add the holes. To finish adding these holes, I can turn off the point tool by clicking its icon on the toolbar, or by pressing Escape on the keyboard. Pressing Escape on the keyboard simply deactivates the point tool and will not exit us from the Hole Wizard feature. To accurately define the position of the holes, we'll be using dimensions and relations, just as you've seen in every other sketch up to this point. To get a better view, I'll look normal to this sketch by pressing the spacebar on the keyboard and clicking the Normal to View option. At this point, with the selection arrow, I can click and move the points anywhere. So let's use a combination of relations and dimensions to make these two holes horizontal from one another. I'll hold down the Control key to select both of them. Select the horizontal relation from the pop-up, and you can see the holes snap into position. I'll repeat this process for the lower two holes, and you can see that these two sets of holes remain horizontal from one another, as well as the geometric flags being added. Next, I'll hold down the Control key, choose to make these 2 points vertical, and repeat the process for these holes here. At this point, you can see the relations that are added, so I'll simply need to add a couple of dimensions to finish fully defining the sketch points. I'll launch the Smart Dimension tool by pressing the S key on the keyboard. And if I add a 15mm dimension to this hole here, you can see that this hole updates as well, since it has a corresponding vertical relation. I'll repeat the process for the opposite side. And if I press the Escape key on my keyboard, you can see that these holes can no longer move side to side, but they can still move up or down. I'll finish by adding 2 more dimensions using the S key on the keyboard, and give a vertical dimension from this edge. And 1 more vertical dimension from this edge to this point. To exit the Smart Dimension tool, I'll press Escape on the keyboard. Now at this point, the status bar indicates that the sketch points are fully defined, and so I'll click the green check to finish. When I do, you can see the 4 holes are added. And there's a new Hole Wizard feature in the Feature Manager tree. If I expand this Hole Wizard feature, you can see there are actually 2 sketches here. The first sketch shows us the sketch points that we use to define the locations of the holes, and this second sketch here is one that Solidworks created automatically. Solidworks uses the second sketch as the basis for the shape of the hole to define its type. If you want to change the hole type, size, or shape, I recommend never editing this second sketch. Instead, it's always a better idea to edit the Hole Wizard feature itself. To do this, just click on the feature and select Edit Feature. Here, you can choose from all of the standard hardware types, and if you want to modify the position of the holes, you can simply switch over to the Positions tab. I don't need to make any changes here, so I'll click the red X icon to exit the Hole Wizard command. To complete this bracket component, we'll be working with the Fillet feature to break all the sharp edges on this model. Before I begin, I would like to quickly mention a few rules of thumb that are good to keep in mind when it comes to fillets. Generally speaking, it's a good idea to save adding cosmetic fillets until the end of the part. Second, I recommend creating larger fillets first, and then creating smaller fillets after. As your models become more complex, you may have areas where one fillet feature may overlap with another filleted area. When this is the case, there can sometimes be geometry conflicts that exist, but by creating the larger fillets first, this will sometimes help you avoid those geometry conflicts. Finally, I recommend grouping fillets together in the same feature if they are to be the same size. I'll show you what impact this can have in just a minute. To begin, we'll be breaking these 4 edges here using one large 10mm fillet, and we'll move on to create all the smaller fillets around the model. I'll launch the Fillet feature from the Features toolbar, and the Property Manager appears. The Fillet feature includes this Manual tab, along with Fillet Expert. Here, we have quite a few fillet types to choose from. Unfortunately, I won't go into all these options here, as most of them are beyond the scope of this course. But most of the time, you'll simply be working with the Manual tab using a constant radius fillet type. With the constant radius fillet type, I can simply type in the radius here, and notice that the blue selection window is active, asking me to select edges, faces, features, and loops. For the first fillet feature, I'll begin selecting these edges around the model. When I do, you can see the preview appears. In case you don't see this preview, notice there's an option here in the Property Manager to display the full preview. As I'm selecting edges around the model, notice that with this edge back here, Solidworks actually lets me select it without having to rotate the model. This is often very convenient, letting you select edges directly through the model without continuously having to rotate. Also notice that Solidworks provides this flag here in the graphics area, giving you another way to type in a radius value. I can click right here to highlight the selection, type in a value, and press Enter once on the keyboard to see the preview update. I'll switch this back to 10mm for our example. Press Enter once to update the preview, and if I press Enter again, Solidworks will finish the Fillet feature and exit the command. The fillet is now added to the Feature Manager tree, so I can continue on with the next fillet feature. Now, instead of launching the Fillet command from the Feature toolbar again, I'd like to show you a convenient shortcut. In cases where you want to launch a command that you are just working with, you can simply press the Enter key on the keyboard to have Solidworks relaunch the last command that you are working with. If you've worked with AutoCAD in the past, you'll probably find this shortcut familiar. Once the fillet feature is relaunched, we'll again select the constant radius fillet to create the smaller fillets. This next fillet feature will have a 3mm radius, and I can select the geometry that I'd like to fillet. Instead of choosing the outer edges of the model, notice that if I select this top face of the model here, SolidWorks selects all of the edges that are adjacent to it. Unfortunately, that includes these circular edges here, which I don't want to fillet. So, instead of selecting the face, I'll select the edges around the model instead. To remove the face from the selection window, I can highlight it and press Delete on the keyboard. But another way to do this is simply by clicking it again in the graphics area. By clicking it in the graphics area, you can toggle it in and out of the selection window. I often prefer this method because it's oftentimes easier to identify selection graphically than it is by the designator of Face 1, or in some cases, maybe Edge 23, and so on. In this case, I'll remove the selection from the graphics area by highlighting it from this window and pressing Delete. Now instead of using the face, I'll select this edge here. When I do, notice that several other edges were highlighted. This is because of an option in the Property Manager called Tangent Propagation. With this option activated, any edge that is tangent to the original edge that I selected will have the fillet applied. Next, I'll select this edge here, and you can see the tangent propagation brings the fillet all the way around the tab. I'll select another edge here, and a couple of the interior edges of the tab. Finally, I'll select these two edges here, and I'll go ahead and click the green check to finish the feature. Now I mentioned that it's a good rule of thumb to group similar sized features together in the same feature. The reason this is convenient is because if this fillet size ever needs to change, you can simply make a change to one fillet feature. For example, when I edit this fillet feature, I can simply type in a new value, click the green check, and see that all of the filleted edges are updated together. At this point, you've learned about the sketcher, taken a look at individual features, and we've gone over some of the principles that are important when creating parts. What we have yet to do is actually create a part from scratch and combine everything learned so far. In this exercise, we'll start building real parts, so you can see what the step-by-step process looks like. Because this is the first part we're going to build from scratch, it's important that I start with a short disclaimer. Although I will be showing you one approach towards building these parts, and will employ a specific set of features to create them, it's only one of many possible methods. There will always be more than one way to correctly design any part in SolidWorks. As you develop more experience with SolidWorks, you will come to understand that there are certain approaches that are more practical and efficient to use when modeling. But as a new user, don't fall into the trap of worrying too much about what the best process is. The best and most efficient methods will become apparent with time and practice. That being said, let's get started. To give an overview of how I created this part, I'll use the rollback bar to step through each feature. I'll roll back to the top of the tree, and you can see that this boss extrude is the very first feature I decided to start with, and it is based on this sketch. Let me point out here that there is another method that could be employed to get this initial basic shape. Rather than sketch this profile with an angled edge, I could have used one big rectangular block, and then used an extruded cut in the shape of a wedge to create the sloped face. So you can see that there are already two different approaches that could be used to create this simple part. Following the first feature is a through hole, a chamfer on the hole, and extruded cut, and a fillet to round out its edge, another extruded cut, and another fillet feature used to break the corners of the part. Notice that compared to the through hole and the rectangular cut, this cut is an interesting case. The other cuts go into the face perpendicularly, while this cut does not. We'll take a look at how you can accomplish a feature like this when you don't have a very obvious face or plane for a sketch. Let's start a new file and walk through the step-by-step process of creating this part. The first question you want to ask yourself when beginning a part is which feature to start with. As you saw in this example, I'm going to start by capturing most of the solid geometry in just one extrude feature. My first step is to select the feature I'd like to create, and because I've chosen to create an extrude, which is a sketch-based feature, I must first select a plane to sketch on. I'll select the front plane. Now that I'm in editing sketch mode, you can see that the sketch tools have become active in the command manager. On the front plane, I'll sketch the profile that I need and add dimensions. Three inches on the bottom, 2 inches, 1.5 inches, and 0.75 inches for the remaining side. Notice that all the sketch entities have changed from blue to black, and the status bar reports that the sketch is fully defined. I'll now exit the sketch, and the Boss Extrude Property Manager becomes available. I'll extrude the sketch to a depth of 5 inches. Using a blind end condition, click OK, and the feature is complete. Earlier I mentioned that there were two different methods that could be used to create this simple shape. A common approach that beginners often take would be to start with a block and then cut the corner off. There's a reason I don't take this approach. If I open a new file, create a block, and create a cut feature. You can see that even though I've just created the same basic shape, it took two features to accomplish, while it can be easily done with just one. Let's continue on with the second feature. This will be the through hole. I'll select the extruded cut command, and rather than select a plane, I'll select this face to sketch directly on it. I'll create this feature using the same basic steps as before. First, I'll sketch the profile of the hole and add dimensions. A 0.8 inch diameter, 0.75 inches from the long edge, 1 inch from the short edge, and the sketch is fully defined. I'll exit the sketch to set the feature parameters. Remember that this hole is meant to go all the way through the part. Right now, the blind depth is set to a depth that extends through the part, but what would happen if a design change caused the thickness to increase beyond the depth set here? The hole would no longer go all the way through the part. It is better to use a through-all end condition to ensure that the hole will always go through the model, no matter what the thickness. This allows you to incorporate design intent into a model. After the hole is created, the next step is to add the chamfer to the edge. Remember that the chamfer is an applied feature, so I don't need to create a sketch. I'll simply select the edge and select the chamfer icon from the pop-up toolbar. In the Property Manager, I'll set the distance to 0.2 inches and the angle to 45 degrees. I'll click the green check, and the chamfer is complete. I'll switch over to the completed part to see what features are left. Next, I need to create this cutout. Notice the rounded edge here. Once again, I'm at a crossroad and have to choose how to achieve this. I can either design the rounded edge into the sketch of the cut, or I can use a rectangular sketch and then round out the corner with a fillet. In this case, I'll use a fillet to create the rounded edge. I'll start a sketch on the top face and switch to a normal view orientation. Using the rectangle sketch tool, I can quickly create the rectangular sketch of the cut I need. Add dimensions of 3 inches and 0.75 inches. I'll extrude the cut 1/2 inch and click OK. I'll select the edge to fillet, select the fillet feature from the pop-up toolbar, and enter a radius of 0.5 inches. The preview looks good, so I'll click OK, and the fillet is complete. The next feature that we're going to create is the slot. Notice that the slot isn't sketched on this face. I'll switch to a wireframe view to make this clear. If I were to put the sketch on this face, the cut would not come down vertically. It would instead extrude normal to the angled face. This isn't the result I want, so I'll need to take a different approach. Let me show you how that's done. Instead of starting a cut extrude on this face, or worrying about creating new planes, I'll start a cut on the same top face I sketched the other cuts on. Even though the face is not directly above where I want to place my cut, Solidworks considers it an infinite plane when it is selected for sketching. Because of this, I can create sketch geometry out in free space. What's happening is that I'm sketching on the same level as the face. So whenever you sketch on a face, keep in mind that the sketch geometry itself does not have to be confined to that face. It can be sketched anywhere on the infinite imaginary plane. I'll switch to a normal view orientation. The shape I want to cut out is quite simple. I'll first sketch a line coincident to the edge of the part, and then use auto transition by moving my pointer back to the end of the line, and out again to create an arc. When I place the end point of the arc, the line tool is automatically active again. I'll close the profile with the final line. Keep in mind that you have to completely close the profile to create this cut, so don't forget the final line segment. I'll add a 0.63 inch dimension to one of the sides, and a 1/2 inch dimension to the arc. At this point, if I drag the sketch, you can see that it isn't fully defined and still has freedom to move along the edge. One of the design requirements for this part is to center the cutout on this edge. I want the slot to be exactly in the middle of the part. So what are my options to do this? Well, this edge is exactly 5 inches long, which we defined in the first feature. So I could very well put in a dimension from the edge to the center point of the sketch, and dimension it to 2.5 inches, and the sketch is perfectly centered. However, if you recall from the earlier lesson on design intent, this would not be a very intelligent way to model the part. What will happen in the future if I need to change the length of this block to something other than 5 inches? This dimension would remain at 2.5 inches, which means the cut would no longer be centered on the block. Instead, there is a better way to center the sketch. I can use a center line as construction geometry. I'll first delete this dimension and select the Centerline tool from the Line tool dropdown. I'll start the centerline at the midpoint of the edge. I'll find the midpoint by hovering my cursor while the sketch tool is active until the point appears. I'll sketch the line horizontally across the part, and the centerline is pinned to the midpoint of the edge because of the automatic midpoint relation. How does this help me? Well, now I can take the center point of the sketch and simply drag it over to the centerline. Cursor feedback appears, letting me know that I am directly on the line, and Solidworks automatically creates a coincident relationship between the point and the line. This sketch is now fully defined, and I've captured the relationship I was looking for. When I create the cut, I don't want to use a blind end condition to define a specific depth because I want the cut to come up to this edge. I'll instead use the up to vertex end condition. This allows me to select either a point or an edge as the end condition for this cut. This allows me to build in design intent and is a much more robust way of modeling because no matter what happened to the size of the block in the future, this cut will always go just up to the edge. There is one last feature necessary to finish up this part, the fillets that go around the 4 corners. I'll add them using a single applied fillet feature. I'll select the edges, and remember, you can select the edges through model geometry and set the radius to 1/2 inch. I'll click OK, and the part is complete. Making use of symmetry when modeling parts can save time and simplify design changes. This part, for example, has symmetry across the top plane, meaning it is exactly the same on the upper half as it is on the lower half. You can see that it has the exact same features, the rounded base, extruded boss, and 2 holes on either side. Because of this, we can design half of the part and use the mirror feature to generate the other side. First, I'll create a new part file. Make sure the units are set to inch, pound, second, and set the material to plain carbon steel. I'll start by creating the sketch of the first base extrude on the front plane. I'll sketch a vertical line coincident to the origin, and use auto transition to create the arc. I'll also make sure that as I sketch, the vertical, horizontal, and tangent relations are automatically created. Now, I'll add dimensions. 3.5 inches for the vertical line, and 0.75 inches for the radius of the arc. Now that the sketch is fully defined, I'll launch the Extruded Boss feature from the Features tab. Using a blind end condition, I'll extrude the sketch 1/4 inch. I'll click OK, and the base is created. Next, I'll create a hole wizard hole on top of this rounded face. I'll select the face, and launch the hole wizard feature. This design uses a countersunk hole type, using the ANSI inch standard. The type will be a 100-degree flathead screw, with a 1/4 inch diameter. And I'll use a through-all end condition so it goes through the entire part. I'll switch to the Positions tab, and click the face to place the sketch point for the hole position. Notice that the sketch point is shown in blue, indicating that it's underdefined. To fully define the sketch point, I'll add a concentric relation between the point and the arc of the base. I'll click OK, and the hole is added. Next, I want to focus on the tombstone-shaped boss. There are several ways to approach this. The simplest method, in this case, is to start with a block, extruded up from the front face of the base. I'll start a sketch on the front face of the part. I'll sketch a rectangle and dimension the sides, 0.5 inches and 0.75 inches. I'll also make the bottom edge of the rectangle 2.5 inches from the origin. All that is left to do is decide how to center the rectangle with respect to the rest of the part. You can see that if I click and drag the sketch, it's free to move from side to side, even though its dimensions are defined. To center the sketch, I'll use a piece of reference geometry, a center line, to connect the midpoint of the bottom of the part to the midpoint of the lower sketch segment. I'll add a vertical relation, and the sketch is now centered and fully defined. I can now extrude the sketch 1/2 inch, and click OK. Now that I've created the foundation of the boss, I'll start a sketch on the top face to create the rounded portion of the tombstone shape. The best way to do this would be to use a tangent arc to create the rounded shape. But Solidworks requires you to first have a sketch segment to connect it to. To get around this, I'll first sketch a line segment along the edge of the boss. And now, I can use the tangent arc tool to create an arc that is perpendicular to this line. The sketch is fully defined, so I'll create the extrude. It's always a good idea to switch to an isometric view and make sure the extrude is going in the right direction. I know I want the extrude to always be as thick as the block, so rather than using a blind depth, I'll capture this design intent by using the up to surface end condition. I'll select the bottom face of the block as the end surface and click OK. Now that the boss is fully created, I can make the next feature, the hole wizard hole on this top face. I'll select the face and launch the hole wizard. This hole is going to be counterbored, again using the ANSI inch standard. I'll set the type to socket head cap screw and the size to 1/4 inch. The end condition will be up to surface, using the bottom face of the boss as the end surface. I'll switch to the Positions tab, and I want the hole to be concentric to the arc of the boss, so I can either place the point and add a concentric relation as I did for the previous hole, or if I hover over the edge of the arc, you can see the center point of the arc wakes up, and I can place the sketch point directly on it, creating a coincident relation that will keep the hole concentric to the arc. I'll click OK, and the hole is added. At this point, half of the model is complete. To create the rest of the part, I'll launch the mirror feature. Instead of using a plane as the mirror reference, I'll use the bottom face of the part. I'm not going to mirror features or faces in this case. I'll instead activate the Bodies to Mirror selection box and select the body in the graphics window. You can now see a preview of what the result will be. I'll accept this, and the model is complete. You can see how designing half of the model and then mirroring it is efficient and captures my design intent. If I take a look at the mass properties on the Evaluate toolbar, you can see that the center of mass in the Y direction is equal to 0, indicating that this part is perfectly symmetric about the Y-axis. If I decide to make a change to the part, for instance editing the dimensions of the first sketch, all I have to do is make the change here, and the other half will automatically update. If I again check the mass properties, you can see that the center of mass in the Y direction is still 0. While this approach is very powerful, there might be cases when you wouldn't want to use it. For instance, if I don't need to have the counterbored hole on both sides of the part, I can take a different approach to build some flexibility into this part, allowing me to choose which features I do and don't want to mirror. Now let's take a different approach to modeling this part. I want to incorporate symmetry from the very beginning at the sketch level. I'll create a sketch on the front plane, just like before. But instead of closing this sketch with a sketch line, I'll instead use a center line. I'll add the same dimensions as before, 3.5 inches and 0.75 inches. Now, if I select all of the geometry, including the center line, and click the Mirror Entities tool on the Sketch tab, the sketch is mirrored. I'll extrude the sketch 1/4 inch. Click OK. And now I have the base of the part created. Next, I'll add the countersunk hole at the top. Once again, it is a 100-degree flathead screw. 1/4 inch. Through all hole. Centered with respect to this arc. Once the hole is created, I'll sketch the block on the top face, and dimension the height and width. When I try to dimension the distance, notice there is no longer an edge to dimension to. In this case, I can either add a center line to dimension to, or dimension to the origin. I still have the challenge of centering the sketch to keep it from moving side to side. Like I did before, I'll use a center line. I'll attach the center line to the midpoint of the sketch segment, and then hover over the circular edge to wake up the midpoint of the arc. I'll add a vertical relation to the line, and the sketch is centered and fully defined. I'll extrude the sketch 1/2 inch. Make sure it's going in the correct direction, and click OK. Next comes the rounded part of the boss. I'll sketch it as I did before, but this time I'll use Auto Transition to quickly switch from the line tool to a perpendicular arc. Extrude the sketch up to surface, using the bottom of the block as the end surface. The final step is to put the counterboard hole in the boss. Recall that it's a socket head cap screw, 1/4 inch diameter, with an up to surface end condition, and its position concentric to the arc. Now I have to deal with the symmetry of the part. You can see that I need to mirror the tombstone-shaped boss and the 2 hole features. To do this, I'll use the same mirror tool as I did in the previous example, except this time, I'll use the top plane as the reference. And instead of using the bodies to mirror selection box, I'll enable the features to mirror selection box. I want to select the features from the feature tree, which I can access by expanding it here, or by clicking on the banner at the top of the property manager. I'll select the 2 features that make up the boss and the 2 holes. I'll click OK, and you can see that the part is exactly the same as the first example. The advantage of mirroring features instead of a body is that if you decide you don't want the part to be perfectly symmetric, you can simply edit the mirror feature and remove it from the selection window. For instance, to remove one of the holes, I'll edit the mirror feature, delete the hole wizard feature from the selection window, and click OK. Now let's take a different approach to modeling this part. I want to incorporate symmetry from the very beginning at the sketch level. I'll create a sketch on the front plane, just like before. But instead of closing this sketch with a sketch line, I'll instead use a center line. I'll add the same dimensions as before, 3.5 inches and 0.75 inches. Now, if I select all of the geometry, including the center line, and click the Mirror Entities tool on the Sketch tab, the sketch is mirrored. I'll extrude the sketch 1/4 inch. Click OK, and now I have the base of the part created. Next, I'll add the countersunk hole at the top. Once again, it is a 100-degree flathead screw, 1/4 inch, through all hole, centered with respect to this arc. Once the hole is created, I'll sketch the block on the top face, and dimension the height and width. When I try to dimension the distance, notice there is no longer an edge to dimension to. In this case, I can either add a center line to dimension to, or dimension to the origin. I still have the challenge of centering the sketch to keep it from moving side to side. Like I did before, I'll use a center line. I'll attach the center line to the midpoint of the sketch segment, and then hover over the circular edge to wake up the midpoint of the arc. I'll add a vertical relation to the line, and the sketch is centered and fully defined. I'll extrude the sketch 1/2 inch. Make sure it's going in the correct direction, and click OK. Next comes the rounded part of the boss. I'll sketch it as I did before, but this time I'll use Auto Transition to quickly switch from the line tool to a perpendicular arc. Extrude the sketch up to surface, using the bottom of the block as the end surface. The final step is to put the counterboard hole in the boss. Recall that it's a socket head cap screw, 1/4 inch diameter, with an up to surface end condition, and its position concentric to the arc. Now I have to deal with the symmetry of the part. You can see that I need to mirror the tombstone-shaped boss and the 2 hole features. To do this, I'll use the same mirror tool as I did in the previous example, except this time, I'll use the top plane as the reference. And instead of using the bodies to mirror selection box, I'll enable the features to mirror selection box. I want to select the features from the feature tree, which I can access by expanding it here, or by clicking on the banner at the top of the property manager. I'll select the 2 features that make up the boss and the 2 holes. I'll click OK. And you can see that the part is exactly the same as the first example. The advantage of mirroring features instead of a body is that if you decide you don't want the part to be perfectly symmetric, you can simply edit the mirror feature and remove it from the selection window. For instance, to remove one of the holes, I'll edit the mirror feature, delete the hole wizard feature from the selection window, and click OK.